Okay, so in the last class, we discussed about three-noded triangle element or CST element, and in the CST element, uh, we learned how to determine its element stiffness matrix, and as it turned out that the integrand itself being a constant, because the Jacobian was constant, uh, the gradient of the shift functions were constant. So we could get the closed form expression very easily for the CST element. Okay, so today we would be discussing about, I mean, in the beginning, we would be discussing about the element force vector. Now, the element force vector, as we know, is composed of three components. I mean, not components, there are three parts. So, one is the obvious reaction force or residual forces. Now, this is mostly an empty vector, that means the vector of zeros, except for the ones for the degrees of freedom wherever the our finite element model has been constrained. Except for those degrees of freedom, it is mostly empty. Now there would be another force vector coming from the distributed load. Okay, now I'm not going into that, and mostly we'll try to avoid anything with this sort of distributed force. Then uh, then the next comes your concentrated forces, so like point loads, so so that we know how to handle. So whatever concentrated force has been applied to a geometry, okay, let's say this is your geometry, and this has been divided into several CST elements, let's say. Okay, and at some location you are applying a concentrated force of P, and you know that that should correspond to a given node. Okay, now once the element stiffness matrix has been found out, then you assemble the element stiffness matrices into global matrix. Okay, and when you are solving the global problem, that's where you apply this P. Otherwise, you do not know whether to put this P for this element or the other element, because this only appears once in the global system of matrices. Okay, and so the next category of forces is the traction forces. Okay, or the ones resulting from a distributed load. Now imagine this is our element 1 2 3 physically. Okay, so this is the element number 1 1 2 3 at the node numbers, okay, in the physical plane. And now the traction, or if one of the sides has traction, okay, so that traction will be uh, can be in arbitrary direction, but whatever direction it might be in, I can always resolve that into x component and y component. Okay, so here we are taking an example where there is some traction t, let's say changing linearly from node number 2 to node number 3, acting in x direction. So t is tx0, and tx is let's call it t2, and let's call it t3. So it is going from t2 to t3, okay, along this side. Okay, so so I can write this is basically t2 times n2 plus t3 times n3. Okay, so we'll come back to this, but before going into the further detail, now you might recall in one was xi, in two was eta, and in three was 1 minus xi minus eta. Okay, now we'll come back to that, but so I should draw the ideal triangle. So this is the xi coordinate, this is the eta coordinate, this is 0 0, and this one is 1 0, this is 0 1. So this is all, this is in natural coordinate system. Okay, and this is let's say node number 1, this is node number 2, and this is node number 3. Okay, so on the line 2 3 is where I'm applying the traction, and for the sake of simplicity I'm assuming that there is only one component to the traction, that is the x component. Now there could be only y component and or a combination of both. Okay, the treatment is going to be the same for each component. Okay, so now you can imagine that that this traction T over here is applied to line 2 3, and if it is linearly changing from point to node 2 to node 3, so this is what its expression is going to be. But you also need to know that what is the value of xi, because N3 has xi. What is the value of xi on the line 2 3? Can you tell me what is the value of xi on the line 2 3?
To 0.
0, which makes it T2 times eta plus T3 times 1 minus eta. Okay, so basically a linear interpolation, okay, between these two values, T2 to T3, which is quite obvious, right? Achha. Now now the FQ or FT can be written, if you follow the variational formulation that we did, it is going to be N transpose T, the distributed load, okay, then integration over gamma T d gamma. Okay, now d gamma is supposed to represent the surface area. Okay, so d gamma is basically h, the uniform thickness of the geometry, times the differential length, okay, measured along the line 2 3, differential length measured along the line 2 3. Now on 2 3, x is basically x1 into x2 into plus x3 n3. So this is the advantage of using an isoparametric element. So basically same shape functions. Now again, if you use the idea that xi is 0 on the line 2 3, okay, so this basically boils down to x2 times eta plus x3 times 1 minus eta. Okay, no confusion so far, or is there any confusion?
No, sir.
Okay, so now I can differentiate x, and that basically turns out to be x2 minus x3 times eta d eta, right? Can you see this? Is it obvious?
Yes, sir.
Okay, now if I write this statement, would that also be correct? Because you know y is also mapped with the same set of shape functions. Sorry, y2 n2 plus y3 n3. If you recall, x vector was xy mapped through n times x hat. X hat, of course, was this x1 y1, x2 y2, x3 y3, transpose of that. But then n matrix was this quantity, n1 0, n2 0, n3 0, and 0 n1 0 n2 0 n3. Okay, so basically y would also be y2n2 plus y3n3. Okay, so do you agree on these two expressions? Dx and dy will have very similar expression. Do you agree to that?
Yes, sir.
Okay, so differential length is square root of dx squared plus dy squared, which is basically x23 squared plus y23 squared, the way we defined earlier. Now this basically means L23, because this quantity x23 squared and y23 squared, that means x2 minus x3 squared plus y2 minus y3 squared, is basically the square of the length of the side representing 2 3. Can you see that?
Yes, sir.
Yes, sir.
Okay, so d gamma becomes L23 d eta. Okay, L23 d eta times h, the uniform thickness. Okay, okay. Now again recall this expression that t is essentially tx0, which is eta times t2 plus 1 minus eta times t3 0. Now if I integrate this traction over here, okay, so that becomes n transpose t, that is this vector over here, times d gamma, which is h, you can take it outside of the integration, L23 times d eta. Okay, now I made one mistake. Please note that between 2 to 3, okay, if you look at the ideal triangle, so this is 1 2 and 3, between 2 to 3, if you go from 2 to 3, integrate between 2 to 3, eta is actually reducing. Okay, which means, you see, I got dl, which has to be a positive quantity. I got that as square root of x23 squared plus y23 squared. Okay, then I am supposed to get the absolute value of d eta. Okay, because that also was part of the square terms. Okay, then we took it out of the square root. Okay, so I'm supposed to get the absolute value. Okay, so all I'm saying here is, this is the way we can do it. We can either integrate between 2 to 3, okay, and then then take it to be, you see, if it is absolute value, because d going from 2 to 3, okay, if I am integrating from 2 to 3 on the side 2 3, so the d eta is negative. So this basically means that differential area, or for that matter differential length, is going to be negative of this quantity. Okay, So either I do that, or basically I integrate from 3 to 2. In either case, this is what it is going to be. So if I'm integrating from 2 to 3, the limits are 1 to 0. But then if I want to make this negative sign positive, all I have to do is integrate in the reverse. So this is going from 0 to 1, and I'm not also putting any negative sign over here. Okay, so you should be careful, a little bit careful with the sign itself, otherwise you are going to get a negative force vector. এই পার্টটা কি বোঝা গেল কি বললাম, কেন এরকম হচ্ছে?
Yes, sir.
ওকে
স্যার বলছিলাম ওই 1 2 3 টা সবসময় এইরকম করেই আমরা ম্যাপিং করব, মানে যে 2
মানে
to 3 টা
কাউন্টার
একদম
ক্লকওয়াইজ
নেগেটিভ
স্ক্যান করব
হচ্ছে
কিনা, কাউন্টার
না,
ক্লকওয়াইজ
যেমন
করব কিনা
2
সেটা
টা 3 হ্যাঁ ওইটাই,
কাউন্টার ক্লকওয়াইজ যদি না করি, সো দ্য
ওইটাকে
এরিয়া,
আমি পজিটিভ করতে চাইছি।
হ্যাঁ, the counterclockwise যদি না করি, then det j would be negative. Okay, এবার you can either work with det j negative or you can either work with det j positive. মানে তুমি পৃথিবীর সমস্ত ফাইনাইট এলিমেন্ট সফটওয়্যার যতগুলো আছে তাদের সবার জন্য এমন ভাবেই নাম্বারিং করো যাতে করে determinant of Jacobian becomes negative. Okay, now what does the meaning of determinant? In the earlier class we saw that determinant of j was possibly twice the area for the triangle, right? It was twice the area for the triangle for the CST element. In some way or the other, the determinant of the Jacobian, whether it is a 2D element or a 3D element, if it is a 2D element, it represents the area. If it is a 3D element, it represents the volume. Okay, now again in 2D, once you multiply with the uniform thickness, the area becomes the volume. So the determinant of Jacobian essentially represents the volume. Okay, now you can either take all elements numbered in counterclockwise fashion or clockwise fashion, or you can either choose all the elements to be in clockwise fashion. Otherwise what will happen is all the finite element softwares, they use the value of the Jacobian, okay, to assert certain behavior of a nonlinear finite element model while doing a solution. Now right now we are doing a very simple, very linear sort of a problem, but most of the problems are non-linear in finite element method, and that's essentially why you use them. And and the value of the Jacobian or the sign of the Jacobian becomes an indication of how the solution is progressing for the software. Now if you take the convention of, you know, the Jacobian of the you see, you can either consider the determinant of Jacobian to be the volume of the element or the negative of the volume. Okay, that means if you take clockwise, the determinant of Jacobian would be negative of the volume. Okay, that's all I'm saying. But if that is the convention you are working with, okay, that is fine. Okay, that is if all the finite element softwares are working with that thing, that is fine. Otherwise, let's say you are working in a given software which takes clockwise numbering, okay, and the negative determinant of Jacobian as the convention, and then you shift that model to some other finite element software, and that software throws you an error that some elements or most elements or all elements are having negative Jacobian, which is an indication that the element, let's say a simple tetrahedral element, is actually flipping. Okay, now what is flipping? Let's say this is your tetrahedron. Okay, this is a tetrahedral element. Somehow this node is trying to penetrate this surface and going to the opposite side. That's what is flipping. And in order for an element to flip, there has to be a situation where the volume becomes zero. Okay, physically the volume can never be zero. Okay, and therefore that becomes a warning for the finite element software that there is some error that is going on, there is some problem that is going on with the solution. Okay, and that the solver determines through the change in sign of the Jacobian. Okay. Now typically, if a software uses the positive value of the Jacobian, okay, to be the convention, that is counterclockwise numbering as the convention, then it will throw an error when it gets a negative value of the Jacobian. Okay, and that can happen in two ways. One is while doing the solution, you are getting calculations which indicates that this element has been flipped. Okay, then the solver takes a smaller time step and does the solution. The other thing could be that you are using a different numbering, that is a clockwise numbering. Okay, and then you get an indication of a problem which is actually not there. The element might not be flipping through calculation, but the solver thinks there is an error. Okay, so you can either work with one set of convention or the other one. Okay, and mostly people agree on, all the softwares agree on counterclockwise numbering and the positive value of the determinant of the Jacobian. আমার পয়েন্টটা কি ক্লিয়ার হলো এই অবধি বলে?
হ্যাঁ স্যার।
আচ্ছা, anyways, so the integration goes from 0 to 1. I mean, either way, whether you do the integration from 2 to 3, okay, then you'll have to take this to be minus d eta, or you can do it from 3 to 2, then you don't have to do any change, because between 3 and 2 the eta is changing positively, and then differential length is the absolute value of d eta is essentially d eta. Okay, so either way, this is what the final expression is going to be, or not the final, but the rather simplified expression is going to be, and then we can do the integration. Now, if you think about this, you see your the matrix of shape function over here. Now this is your matrix, right? n1 0, n2 0, n3 0, 0 n1, 0 n2, 0 n3. Now what is the value of n1 on the line 2 3?
0.
0.
0.
0. Yes, that is by definition. Now what is the expression of n2? Eta. And what is the expression of n3 on the line 2 3?
1 minus eta.
1 minus eta, and you don't have to bring in xi. Okay, so take the transpose of this quantity, multiply with this vector, which basically has two components, one of them non-zero, the other one is 0. Okay, and then perform the integration. Okay, so can you do that now? Can you get the expression? এই ইন্টিগ্রেশনটা করতে পারবে তো? করে ফেলো তাহলে। Then can you tell me what is the expression of the force vector? I mean, I can see h and l by 2 3 coming out of the integration. And if this is the force vector, I can also see that that the first two terms are 0. Then third term is non-zero. Fourth term is 0 because it is a y component. Fifth term is non-zero, and the sixth term is 0. So can you tell me the expression for this term and this term over here?
T2 by 3. Third down. Hello.
Sir, sound is not coming.
Sir.
Is it something like this?
Yes, sir.
Okay. Now it's a trapezoidal sort of a loading, right? Okay. So how much is the net force coming out of this sort of a loading? Is it not T2 plus T3 by 2 times H times L23? Is it not going to be the total force coming out of this traction? It's a trapezoidal loading on the surface, right? So can you see this is how much the net force should be? And actually, if you add the two components here, you will see there is a net force that you are getting in the x direction. Okay. So through finite element formulation, the net force you are able to capture correctly.
স্যার উপরের রেজাল্টটা কি করে আসলো এই T2
কি
প্লাস
করে এলো
T3
কি করে এলো
মানে
মানে
হ্যাঁ
আমি যদি ধরো এইটা হচ্ছে the length, ঠিক আছে, I mean the distance measured along 2 3. Okay, so if it is the coordinate along 2 3, ঠিক আছে, so so one part the traction is T2, then on the other side it is T3. Now physically, on the physical geometry, the traction need not be normal to the edge. All I'm trying to show here is that if I were to plot it, the x-axis as a coordinate measured along 2 3, and y-axis the traction value. Okay, now the net force in the x direction is obviously the area under this plot, right? And that
Yes, sir.
area is the area of the trapezoid. And how much is the area of a trapezoid? You add the two side lengths, okay, take the average of that, basically take the average value, okay, and multiply with the distance between the two parallel lines, right?
Yes, sir.
Okay, so that way I'm doing how much is the distance along line 2 3 L23, and this is how I'm getting the expression for the total force. Is it clear now?
Yes, sir.
Okay, so in the end this is the expression that you get. And what you can do is, let's say, for imagine if T2 equals T3 equals T star, okay, you'll get the same force values at the two nodes. Okay, so basically the odd slots are the x components of the force on a given node, and the even slots are the y component of the force on a given node. Okay, so the x component of the force on node number 2 and x component of node force on the node number 3, they will be identical if the traction were to be uniform. এটা বোঝা গেল তো?
স্যার একবার
Yes,
বলুন।
sir.
যেটা বললাম যে if you substitute t2 equals t3 equals t star, that would imply that the traction itself is uniform. There is no variation from node number 2 to node number 3. Okay, then you would get the same force value, okay, which is basically even half of this. Sorry, yes, it is going to be t star. It is going to be, let's say, then the net force is going to be h times L23 times t star. Okay, and half of that would apply to node number 2, and half of that, the remaining half, would apply to node number 3. That's all I'm saying.
Okay, sir.
Okay, acha. So now you know how to get the force coming out of a traction in x direction. Now, instead of applying in x direction, if I were to apply this traction in the y direction, okay, if this would look like something like this, 0, and over here eta times t2 plus 1 minus eta times t3, how would the force vector look like? If I were to change that there is no traction in x direction but only traction in y direction, graphically this is how it would be. What would be the expression for the force vector? What change would happen?
স্যার 4 আর 6 নম্বর এলিমেন্টটাতে এই দুটো ভ্যালু আসতো।
So instead of it being 0 0 non-zero 0 non-zero 0, okay, the expressions are going to be same, but only thing is the positions will change, right? So that would be 0 0, then the third component is also 0, and then the fourth component is non-zero, and that would be the value. Then the fifth component is 0, and then the sixth component is this value. Is it clear now?
Yes.
Okay.
Yes, sir.
Acha. Now again think in terms of linear superposition. If I were to have both tractions in x and y direction, and this time I'm putting superscript to represent in which direction it is. So t2x plus 1 minus eta tx3, how would the force vector look like? So the force vector will have 4 non-zero components. Okay,
0 0.
so this is how it is going to look like. This is going to look like something like this: 0 0, then twice t2x plus tx2 plus tx3, then twice ty2 plus ty3, then tx2 plus twice tx3 plus ty2 plus twice ty3. Okay, so can you think of this to be the result? Can you imagine how this is going to be possible? Since it's a linear system, okay, you can do linear superposition, and you can identify how the final expression is going to be with traction in both direction. Okay, basically the traction being not in either in x or y, being an oblique traction, and having components in x and y. Okay, so I hope you can understand this part. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay, now we would proceed for 4-node quad element. So the CST element has the following terms defining its you see your shape functions. So the shape function of the CST element has either 1, xi, or eta, and this is what constitutes the shape functions of a CST element. Hence, the CST element is called a linear element. It is linear in xi and eta. Okay. Now, in the CST element also, here we see 3 nodes. We can try to make it quadratic, and we'll have further nodes like 4, 5, 6. Okay. And then we would probably encounter higher order terms. Okay. So that is for 6-noded triangle element. Okay. So this thing that I'm drawing, so this triangle that I'm drawing here with the possible terms in the shape function, this is known as Pascal's triangle. Similarly, in 3D, there is Pascal's pyramid, okay, involving another natural coordinate, let's say gamma. Now, 4-noded quad element works with this set of terms. You see, there are 4 nodes, 4 shape functions, hence 4 polynomial terms. Okay. So just like in 1D, if you are to work with 3 nodes, remember 3-noded bar element, so there would be 3 shape functions, and the shape functions should have terms like C0 times 1, that is xi to the power 0, then C1 times xi plus C2 times xi squared. Okay, this is how the individual shape functions must look like, quadratic shape functions. So you require 3 terms for 3 nodes. 4-noded quad element has basically looks like this. Okay, it has 4 nodes. Okay, and therefore it requires 4 shape functions, and each shape function should be composed of with one or multiple of these 4 terms. No other term would be required. Okay, so this is for 4-noded quad element. Okay, and 4-noded quad element is called a bilinear element. Now, what is the difference between linear and bilinear? Please note that you are incorporating a term xi eta, okay, which is not a linear term, which is a 2nd-order term. But 4-noded quad element is individually linear to xi and linear to eta, but not together. Whereas CST element is the shape functions like N3 in CST element is 1 minus xi minus eta. So it is linear in both xi and eta. Okay. But in 4-noded quad element, we would see that the shape functions that we encounter that are not completely linear in xi and eta. They are individually linear in xi or individually linear in eta, but not together. That means if you fix one of the values, it is linear in the other, but not simultaneously. What I mean by that, for that we need to construct the quadrilateral in the natural coordinate. So this is xi, this is eta. These are the 4 nodes. Okay. And what are the coordinates of those 4 nodes? -1, 1. For CST element, the range was from 0 to 1. But for this one, sorry, -1, -1, 1, -1, 1, 1, and ultimately minus 1, 1. These are the 4 nodes. Now, the way we define shape function is in I, xi j eta j is delta ij. That implies in I, that implies this equals 1 if I equals j and 0 otherwise. So we are already familiar with this, and this is also true. Now, look at node number 1. In 1 is supposed to be 0 on node number 2, node number 3, and node number 4. Okay. That means it is supposed to be 0 on the line 2, 3, and it is supposed to be 0 on the line 3, 4. Now, can you tell me what is the equation of the line 2, 3?
X equal to
Xi
1.
equals 1.
Xi equal to 1.
Xi equals 1. Now, therefore, if I put 1 minus xi, multiplying some other term, okay, so that is this quantity, this n1 is trivially 0 on this line. Can you see this?
Yes, sir.
Now think of line 3, 4. What is the equation of the line 3, 4?
Eta equal to 1.
So if I put it 1 minus xi, 1 minus eta, it is 0 on both the lines. Now it has to be equal to 1 on node number 1. Okay. So then substitute the values of xi and eta in n1, which are minus 1 and minus 1. Then you would realize that I'm supposed to divide this whole thing with 4. Okay. And this is what I mean by bilinear shape function. It is independently linear in xi. When you keep eta equals eta fixed 0 or 1, whatever, it is linear in xi. Same thing applies to eta, but it does have a term xi eta, and you can check these are the different terms that you will encounter in its final expression. If you simply expand n1, these are the 4 terms that you are going to get. Now, can you write down the expressions for n1, n2, n3, and n4? What would be the expression for n2?
1 plus xi
Okay.
into 1 minus eta.
Next.
1 plus xi into 1 plus eta.
And finally,
1 minus xi 1 plus eta.
okay. So we can check that ni is actually 1 by 4 1 minus xi I times xi, 1 plus xi I times xi, 1 plus eta I times eta. Does this general expression fit for all the shape function? Does it fit with all the shape functions?
Yes, sir.
Okay. Now think in this way. Now, does this ring a bell? This sort of representation, 1 plus xi I times xi divided by 2. You don't recall this shape functions, or do you? This
Linear
is
bar
actually,
element.
Linear
yes,
bar element.
linear bar element. So the shape function of linear bar element. So basically, this 4-noded quad element is like having bar element in xi direction and bar element in eta direction. Linear bar element in xi direction and linear bar element in eta direction. Hence the term bilinear element. Okay. And later on you would see the quadratic version of the 4-noded quad element is obviously going to be 9-noded quad element, and that 9-noded quad element is also like quadratic bar element in xi multiplying a quadratic bar element in eta in terms of the shape functions. বোঝা গেল কি বলছি?
Yes, sir.
Okay. So now that we cleared with the shape function, okay, now we do not require any figure this point beyond, right? So what we can do is, the first thing that we need to draw or need to evaluate. Now we will talk about Pascal's triangle in the future classes even more, okay, but for the time being we don't need them. So now what we would do is, of course, we know that let's say x, which represents the coordinate of any location xy, okay, within the, so let's say this is the arbitrary point P within the physical element. So that is essentially your n matrix, which is going to be 2 cross 4 matrix, 2 cross 8 matrix. You see there are 4 nodes, so 8 degrees of freedom and 8 coordinates. Now what are the 8 degrees of freedom? So these are node number 1, 2, 3 and 4. So these are the degrees of freedom: u1, u2, should be using small u, elemental still, u4, u5, u6, u7, u8. Okay. So for u, which is ux, uy, is going to be n times u hat, where u hat is u1, u2 up to u8 transpose, and same thing happens to the variation n times v hat, and this quantity is this times x hat, where x hat is x1, y1, that is the coordinates of the node number 1, x2, y2, and so on up to x4, y4, this whole thing transpose. Basically, it's a column vector. Okay. Now, in order for n matrix to give you the corresponding x and y, n is supposed to look like this: n1 0, n2 0, finally n4 0, and 0 n1, 0 n2, finally 0 n4. Any confusion up to this part?
No, sir.
Right? Because it is going to be exactly similar to what we did for the CST element, except the shape functions are different right now, of different nature, different expression. Okay. Acha. Now, we also learned about that we could represent n in a vector format as well, where it is going to be n1, n2, n3, n4. Okay. And that is essentially the representation that we need when we are trying to get have you written down the expressions for n1, n2, n3, and 4? Can I clear the canvas?
Yes, sir.
Yes, sir.
Okay. So that is the expression that we need when we are trying to get the gradient of the n bar vector with respect to the natural coordinates, which is going to be, individual components are going to be del ni, del xi j, and the size should be, number of rows are determined by the number of shape functions, and number of columns determined by the number of natural coordinates. So all I'm trying to say here is I in 1, 2, 3, 4, because 4 shape functions, and j in 1 and 2, where xi1 basically means xi and xi2 basically means eta. So can you write down the expression for this matrix, gradient matrix?
One by four by the sir. Matrix.
Okay. Then
Minus my eta minus 1. Eta minus 1 মানে minus into 1 ব্র্যাকেটের মধ্যে 1 minus eta.
আচ্ছা আচ্ছা
1 minus eta, the minus ব্র্যাকেটের বাইরে 1 minus xi, 1 minus eta minus 1 minus, then it's a 1 plus eta, 1 plus xi, and minus 1 plus eta 1 minus xi.
Okay, so this is the gradient. And then we would like to calculate the Jacobian, which is defined as the gradient of physical coordinates with respect to the natural coordinates, and individual terms are like del xi, del xij. Now in this case, both I and j are in 1 2 set of 1 2, so it's a 2 cross 2 matrix. Okay, and that for that what we can do is we can write x to be this matrix x1 x2 x3 x4 y1 y2 y3 y4 times n bar, where n bar is again this vector. Okay, we talked about this different representation. Okay, now this quantity individual term can be written as summation over k. K runs from 1 to 4
4 sir.
del xi del nk del nk del nk del xi j. Okay, so what is the meaning of this thing? For example, x1 is actually, okay, please don't confuse with this index with this index over here. This index is for representing the type of coordinate. Okay, these are not nodal coordinates. Okay, and these are, by the way, nodal coordinates. Okay, they are not these are constants for an element, that is these are constants. And this x1 over here or this xi over here, it represents x1 is basically x here and x2 is y, which are changing over the geometry. Okay, so x and y are changing over the geometry. Okay, so that's what this means. So don't confuse the initial notation over with this one. Okay, for example, আমি যদি del x del nk বলি. Okay, now what is the coefficient of, let's say, if I take instead of k, let's say del n3 boli. Now what is the coefficient of n3 that corresponds to, that contributes to x? It is actually x3. So this quantity is essentially x3. Okay, so ultimately what you will see is it is going to be this matrix times the gradient of n matrix. It is J is basically this matrix. So it is 2 cross 4 and it is going to be 4 cross 2. Okay, so ultimately it is going to be your Jacobian. Okay. So can you get the expression for the Jacobian? যে এই অবধি সবাই বুঝতে পেরেছো তো?
Yes, sir.
তাহলে জ্যাকোবিয়ানের এক্সপ্রেশনটা লেখো by multiplying the two sides, the two matrices. আমি ক্লিয়ার করে দিলাম। Okay, and I'll be drawing something on the screen, so please don't do that right now. You try to get the expression for the Jacobian. জ্যাকোবিয়ানের এক্সপ্রেশনটা পাওয়া যাচ্ছে?
পড়ছি স্যার।
ওকে, when you are getting the expression for the Jacobian, also try to simplify it. Okay, so some terms might cancel out, some terms okay. Now don't focus on the the diagram I've just drawn. Okay, I'll talk about it in a minute, but just try to get the general expression for the Jacobian for a general quadrilateral element, an arbitrary quadrilateral element, which in physical space could be anything. Okay, and what I've drawn in black ink is a trapezoid. The actual quadrilateral might as well not be trapezoid.
sir, very yes, sir. Hello.
Okay. Okay. তো কিছু একটা এক্সপ্রেশন পাওয়া গেছে। The point is that is not a constant. Unlike CST element, that is a function of xi and eta. It has terms of xi and eta. তাই তো? ঠিক বলছি তো?
Yes, yes, sir.
Okay. আচ্ছা। Now let's take an example. Let's take this example. Okay. If I take coordinates to be like this, okay, and just for the sake of simplicity, I have taken one of the nodes to be at the origin. Okay, না হলেও কিছু যেতে আসছে না, কিন্তু কারণ ultimately you are subtracting coordinates of one node from the other in every term in the Jacobian. I don't know what is the expression is, but in every term you are essentially doing that. Okay, because essentially the Jacobian represents, in some way it represents the area. Acha, if it does represent an area, why is it not a constant? Now now the reason it is not a constant, the Jacobian is supposed to represent not the area, but let's say in the natural coordinate you take a differential area dA natural, and you take the same area element in the physical coordinate dA. The determinant of Jacobian, which again is not going to be a constant, is supposed to represent dA to dAn. That's what is the meaning of the term Jacobian is. Okay. Now that ratio could be changing from each point to other, and hence there is a possibility of having a you see your non-identical Jacobian. Now when it comes to the CST element, the physical in the physics, since the Jacobian was a constant, then the Jacobian was also the ratio of the A to AN. Now what was AN? Then in the natural coordinate the area was half 1 times 1, which is half. So basically this turned out to be twice the area. Det J turned out to be twice the area. Okay. Now take the example of the parallelogram. Try to get the Jacobian for the parallelogram. You see, once you decide the coordinates of node number 2 and node number 4, for a parallelogram, the coordinates of the node number 3 is already fixed. It cannot be anything but this coordinate. Okay, it's as if to this side you have added the side 1 4, to the side 1 2 you have added side 1 4. That's how you have got to node number 3, you know, the vector law and all. So check what change do you see in the Jacobian? Now this is a general parallelogram.
The half of
So no, I don't need the expression. But tell me, is it still a function of xi and eta?
no, sir.
So you see this A, B, and C and D, these are still arbitrary values. Okay. But just by taking a parallelogram geometry, we have been able to make the Jacobian to be a matrix of constants. Now a parallelogram itself stands for all of these geometries: a square, a rectangle, okay, a rhombus maybe, okay, and any other parallelogram. So for all of these cases, okay, you will have a constant Jacobian. Okay, do all of you are all of you getting a constant Jacobian when you take a parallelogram?
Yes, sir.
Okay. Is there anyone who is not? আর কারা আছে যারা একটা জিনিসও ট্রাই করছো না, একটা ডেরিভেশনও ট্রাই করছো না, তাদের জন্য অল দ্য বেস্ট। Anyways, so the point is the Jacobian is not a constant in general like CST element, but for some special cases, okay, some special cases it can be constant. Okay, now I'll again erase everything from here. So our interest is with this matrix, taking the gradient of the shape functions with respect to the physical coordinates. Okay, so the individual terms are del ni del xj, again a 4x2 matrix. So here x1 is x and x2 is y, and I in 1 2 3 4 and j in 1 2. Acha. So this matrix, as we showed in the earlier class, is a combination of this. So gradient of n with respect to xi multiplying j inverse. If you revisit Wednesday's class, you will see how this turns out to be true. Okay, simply using the chain rule. So this is what you are supposed to get. Now you see, even if the geometry is a parallelogram, okay, where the Jacobian is a constant, this gradient of n is a still function of xi and eta. In general, everything is a function of xi and eta. The gradient of so the individual terms in this matrix are going to be this: del n1 del x, del n1 del y, del n2 del x, ultimately del n4 del x. Here also all such terms, ultimately del n4 del y. These are the terms in this matrix. Okay, now these terms are functions of xi and eta. So this entire matrix are going to be functions of xi and eta, even if the Jacobian is a constant. Okay, so if you look at the gradient of n matrix, each term, okay, is linear in either xi or in eta. Okay, they are no longer bilinear terms after taking partial derivatives, but individually they are either linear in xi or in eta, in gradient of n. Okay, and independent of whether Jacobian is a constant or not, okay, they are still going to be functions of xi and eta. Why am I emphasizing on this? This has one advantage, another disadvantage. So let's first talk about the advantage. Now, if I want to write the strain matrix, which is, you see, uh, comprising of these three terms, which is basically del ux del x, del uy del y, and del ux del y plus del uy del x. Okay, so basically, again, ux is n1 u1 plus n2 u2 plus n3 u3 plus n4 u4, which means del ux del x is u1 del n1 del x plus u2 del n2 del x, and so on up to u4 del n4 del x. Okay, so basically del n1 del x 0, del n2 del x 0, and ultimately del n4 del x 0. This times u hat, where u hat, I keep on repeating this, u1 u2, sorry, this is going to be u3, this is going to be u5, and this is going to be not u4 but u7, u3 u5. So u1 u3 u5 u7, the odd numbers are basically along x direction up to u8 transpose. Similarly, the second row is going to be just like the previous class, and ultimately 0 del n4 del y. And what is the last row going to be? Third row del n1
del y,
del y, then del n1 del x, del n2 del y, del n2 del x, ultimately del n4 del y, del n4 del x. So the point is, just like each term in this matrix were functions of xi and eta, this matrix right now, this matrix is called the B matrix. It is also a function of xi and eta. Okay, so it's a 3 cross 8 matrix. So this matrix is also a function of xi and eta. Even if the Jacobian is a constant, each term in B matrix is at least linear in either xi or eta. Okay, at least a linear function of either xi or eta. Okay, and you can see that that if I take del n1 del xi, it is going to be linear in eta, like 1 minus 1 minus eta. Okay, and in other words, you can also see that if I take del n1 del x, it is going to be linear in y. And how is that advantageous? In the previous class, we were discussing the deflection of a beam. Okay, now let's take an example of a cantilever. You can take any beam, and with a point load at the free end. So at any section, if I were to look at the stress, or for that matter strain, okay, this is going to be high positive to high negative. Now, in which direction is the strain? The strain is in the x direction. So this is basically epsilon xx. If this direction is x direction. Okay. And in which direction is it changing most rapidly? I mean, obviously the bending moment would be changing along the axis, and the strain would be changing along the axis, and the stress would be, bending stress would be changing along the axis, and hence the strain would also be changing. But in y direction, it is going from high positive to high negative. Okay, so the maximum variation is along y direction. Okay, and four noded quad element. Okay, even if the Jacobian is a constant, this quantity is able to model a linear variation of strain in y direction. Linear variation of the strain in x direction, sorry, linear variation of epsilon xx in y direction. It is able to model that. এই পার্টটা কি বলতে চাইছি বোঝা যাচ্ছে? If I were to take CST elements, they are not able to model stress variation at all. Therefore, across the entire thickness, there is going to be a single constant stress value, which you can imagine is some sort of an average. And you know, on a section where the stress is changing from high positive to high negative, the average is very close to zero. So you end up modeling very low stress, giving you very low strain and eventually very low deflection, which makes the finite element structure stiffer than the physical system. Whereas if you use four noded quad element, that is able to model the variation of epsilon xx, which is highly dependent on, you know, derivatives of shape functions in x direction, these terms. It is the four noded quad element is able to model the variation of this quantity along y direction. And when it comes to, let's say, the beam deflection, it is exactly able to model that because the variation is linear. Okay, it is exactly able to predict a linear variation along y direction. বোঝা গেল কি বলতে চাইছি?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. Now the next part. Let me clear the screen. Evaluation of the element stiffness matrix. Acha, by the way, just the same way, epsilon v is b times v hat. Okay, variation of strain. The element stiffness matrix is integration b transpose d bar. Now we need to determine d bar, which is a 3x3 matrix. So this b transpose, so 8 cross 3, and then b 3 cross 8 times d omega. Okay, now d omega is basically your dx dy times h. Okay, so differential area times the thickness, which is the volume. But then this is actually your det j times d xi d eta. Okay, so that's what I'm going to do here. And obviously it is going to be a double integration. And the fun thing, the limits are independent because you are integrating on a rectangle or a square. Okay, so order doesn't actually matter. And also because the integration is from -1 to 1, you get to neglect each of the odd terms over here. So very fun to integrate, right? And also the integrand is not a constant, so you have to integrate. But then there is a problem. So you have your h, det j, and d xi d. Problem is this b matrix, each term in b matrix is linear in xi and eta. Then you have to multiply with d matrix, which is a matrix of constants. Then you'll have to multiply with b matrix. I mean the transpose of b matrix. So in the end, the products are, chances are there will be some terms of xi squared or eta squared. Okay, so, and some of the terms would also be xi eta in the product. Okay, so the thing is, that the highest power of xi or eta could be squared. You can imagine some of the terms are, let's say, the -1 minus eta term, del n1 del xi, multiplies to minus this quantity over here. Each of the terms will multiply each of the terms, right? So there is such a combination also possible. And then that would give you eta squared of a term. Similarly, you will get zeta squared terms. Okay, so you would be getting non-constant terms. Okay, and there would be so many terms, so many multiplication, symbolic calculation, and so many things have to be done, and that makes it very difficult. And all of that is only true when the J matrix is a constant. If J matrix is a constant, the B terms, because you obtain B by from the this matrix, which is basically this matrix times J inverse. Now, if the J matrix itself is functions of xi and eta, so the inverse would be very difficult sort of functions. I mean, there would be rational polynomials. That means there would be polynomials of xi and eta in the denominator. You see, you know, to calculate the J inverse, you need to calculate the determinant, which would be functions of xi and eta, and then that multiplying to gradient of n, which is already linear in xi and eta. So eventually, your B matrix is not even linear in xi and eta. It is some rational polynomial in xi and eta. So linear polynomials polynomials in the numerator, polynomials in the denominator. Okay, something like that. And to be able to physically integrate this is going to be a very difficult job. And hence we use something called numerical integration. Okay, and more about numerical integration in the next class. Okay, I mean next to next class possibly. Now, even if the physical element is not even a parallelogram, just a regular square, they are also, let's say the determinant Jacobian is a constant and determinant of J is a constant, B is going to be linear, but there are so many terms and you will have to perform multiplication of so many terms. So what is preferred is this numerical integration, even for a very regular geometry for a 4-noded quadrilemma. If not regular, then also we use numerical integration. If regular, then also we use numerical integration. Okay, so so we cannot perform the integration for this one using analytical method. We cannot do the closed form integration. Okay, acha. What else? So we'll have to do the numerical integration. Acha. So yes, so that is there. And again, if there is now evaluating the traction force, imagine again there is some traction in x direction. So 1, 2, 3, 4. On the 2, 3 side, there is tx going from t2 to t3. So so just the previous example, tx and 0, and the tx going from t2 times n2 plus t3 times n3, 0. Now you see n1 and n4 are 0 on the line 2, 3. Now what is the expression for n2 in the line 2, 3? For that you need to go to the natural coordinates. You see n2 is like this, 1, 2, 3, 4. So n2 is 1 plus xi by 2, 1 minus eta by 2, and n3 is 1 plus xi by 2, 1 plus eta by 2. Now if you substitute on the line 2, 3, xi is 1, so each of these quantities are 1. So essentially you get the shape functions of a linear bar element. So n2 is 1 minus eta by 2, and n3 is 1 plus eta by 2, and similarly your x is x2 times 1 minus eta by 2 plus x3 times 1 minus eta by 2, which gives us dx equals x3 minus x2 by 2. Okay, just like in a linear bar element, j is le by 2, similar to that, but don't compare that. I mean, don't, just be confused with that. Then dy is again y3 minus y2 by 2. Essentially, the ratio, dl is going to be, as you can see, L23 by 2 times what? D eta. And of course, from 2 to 3, eta is increasing, so there is a positive sign. What is the meaning of L23 by 2? It is basically that Le by 2 over here. Okay, so basically the ratio of the physical length to the length in the natural coordinates of the side 2, 3. That's what that is there. So the next thing is the integration. Ft is basically integration over gamma t n transpose t vector, then d gamma. Now d gamma is dl L23 by 2 d eta. Okay, and n transpose needs to be so because gamma t, so this thing is basically dl L23 by 2 times d eta, and as a d gamma would also have, sorry, d gamma is h times this, not dl. So h times L23 by 2 times d eta, which is dl. So multiply h. Okay. So d gamma is h times L23 by 2 times d eta. So that's what we are going to write here. H times L23 by 2 comes out of the integration d eta, and eta ranges from -1 to 1 as it goes from 2 to 3, and on the line 2, 3, n transpose looks like this. So the first 4 are 0, then the last 4 are also 0. Over here it is 1 minus eta by 2, 0, 0, 1 minus eta by 2, 1 plus eta by 2, 0, 0, 1 plus eta by 2 is your n transpose. You can check that, and you can substitute the expression for t and perform the integration. Okay, and this is going to be your assignment.
স্যার ওখানে x এর এক্সপ্রেশনের সাথে প্লাস হতো 1 প্লাস এটা বাই 2
কোথায় বলো তো?
স্যার x = x2 * 1 মাইনাস ইটা বাই 2, এখানে যে x3 * 1 প্লাস ইটা বাই 2 হবে স্যার। x এর স্যার যেটা এক্সপ্রেশন লেখা আছে স্যার ওখানে উপরে
x এটা, হ্যাঁ
হ্যাঁ
প্লাস হবে। Okay, so you can write down the n transpose. I might be wrong with this expression, but you need to check that and correctly put it over here, and then integrate this. Okay, and see what sort of expression do you get for the force vector, and compare that with, so calculate and compare with the result that you have obtained for the CST element. Okay, so that is your assignment. So calculate the expression for the force vector and compare the values with the CST element. Okay, any queries?
স্যার দুটো টেন্সারের যখন আমরা যদি ইনার প্রোডাক্ট করি ওটা স্কেলার কি করে আসবে, মানে প্রত্যেকটা মানে এই গুণটা কি করে হবে, মানে একটা एग्जांपल।
আচ্ছা শোনো, ইনার প্রোডাক্ট yields স্কেলার, ঠিক আছে। এবার সেটা ভেক্টরের হলে বেসিক্যালি যেটা দাঁড়ায় ডট প্রোডাক্ট, এবং সেটাকে আমরা A ট্রান্সপোজ B বলেও লিখতে পারি when A and B have the same dimension, okay, I mean same length. ধরো যাক A is a 3-dimensional vector, column vector, and so is B. So A transpose B, I mean the matrix multiplication A transpose B is essentially A dot B. এবার ইনার প্রোডাক্ট হচ্ছে একটা জেনারেল টার্ম, ঠিক আছে, and that applies to any sort of vector space, because for any sort of vector space to exist, okay, there has to be an inner product defined on it, and that inner product must have some properties, like A dot A times B dot B should be greater than A dot B whole square. বুঝতে পারছো কি বলছি? মানে আমি ম্যাগনিটিউড অফ A times magnitude of B should be greater than the A dot B, magnitude of A dot B. Okay, বোঝা যাচ্ছে কি বলছি? So just, and we know we can do that for vectors, মানে 3D vectors, position vector, হাবি জাবি এসবের জন্য আমরা যে করতে পারি, that we already know, but that sort of property must exist, and that sort of an inner product must exist for every possible, you know, your functions vector space. And as we have discussed in the very beginning of this course, that the function space is also a vector space, and there is an inner product defined on function space as well. Okay, we have shown that what sort of so that is basically a definite integral across the length, across the, you know, the domain, across the entire geometry, okay, of two functions. Okay, so integration 0 to L, let's say for a bar, 0 to L ux vx dx is basically that inner product. Okay, and if you are to represent the basis functions in Fourier form, let's say cos of x, then cos pi x by L, sine twice pi x by L, and so on. Okay, so we have shown that the inner product of those basis vectors turns out to be 0 if they are not the same basis vector, and if they are same basis vector, you get the maximum value. So we did all of those in the you know, the initial set of classes, okay, of this course, and such it turns out the set of all matrices, okay, of a given dimension. I am talking about square matrices of a given dimension over here, ঠিক আছে। ধরে যাক 4x4, ঠিক আছে, square matrix. So the set of all such tensors, okay, they also form a vector space. They are not vectors in the literal meaning of it, but in the more abstract mathematical sense, what is a vector space? So the matrices also belong to that set, and they have their own inner product, and that inner product turns out to be, you take the two matrices of the same size, okay, matrix A and matrix B. What are you doing here? You take the identically indexed terms, so you take A12 and B12, multiply them, okay, and to that product you add the next term, which is obtained by similar operation, and you keep on doing this exercise until the both matrices are exhausted. So let's say A is a 3x3 matrix and B is a 3x3 matrix. So the A inner product B represented with double dots. Now that double dot also has a different also has a meaning. I have mentioned that already, but I'll do that again. So what you are doing is you take A11 and then B11, multiply them, and then you add with A12 multiplied to, and you keep on doing this exercise, this addition, and up to both the matrices are, you know, exhausted. Now this double dot, so instead of using a single dot, you use a double dot, okay, because for a matrix to do the inner product for a matrix, okay, you need to do a double summation. You go to a given row, and then you take the identically positioned terms, that means identical column numbers, okay, of two matrices and multiply them and keep on adding them. Once you are done with a given row, that means you already did one set of summation, you move on to the next row. Okay, so you change the row index. Okay, so it is supposed to be represented as summation over I, summation over j, aij, bj. Sorry, aij, bij. Summation over I, summation over j, aij, bj. Okay, so there is a double summation. So those double dots come from those double summations. Okay, and in other way of thinking, that is that when you go from couple of vectors to a scalar, okay, because the scalars are zeroth order tensor and vectors are first order tensor, you put a single dot. Now when you take two matrices and get a scalar, so you go from a second order tensor to a zeroth order tensor, so you put two dots over there. Okay, that is one way of thinking, but the more correct way of thinking is when you are doing a matrix inner product, you essentially have to do a double summation. Okay, you will have to go to a given row, then you will have to go for a given column in that given row. Okay, and take the identically positioned components of the two matrices, multiply them, and then add with the next term. Okay, and in order to go for the addition, you need to loop on the column and then you need to loop on the row. Those double summations turn out to be double dots in that representation, a double dot p. বুঝতে পারলে কি বল?
হ্যাঁ স্যার।
আচ্ছা, because we are discussing matrix inner product, absolutely non-required for you, but I'll still show you one important result. A inner product B is summation over I, summation over j. Okay, square matrices, by the way, aij, bij. Okay, and it could also be written as A transpose ji bij. It can be written as summation over j, summation over I, because limits on I and j are independent, like a integration over a rectangle. So definite integration over a rectangle. So I can change the order of summation. So what I'm doing here is A transpose ji bij, basically summation over j, A transpose B you see this summation represents jj. Now what is A transpose B jj? Let's say C is A transpose B and C is this matrix. So you take each of the jj term and add them up. What is that? Trace of A transpose B. এই ডেরিভেশনটা বোঝা গেল? And it can also be shown to be trace of B transpose A. And because
স্যার বলছি ওই aij টা ওই aji ট্রান্সপোজটা কেন হলো, মানে ওটা কি সিমেট্রিক বলে?
না, একদমই না। সিমেট্রিক হলে তো A transpose ij would be, I mean aij would be A transpose ij. Aij is always A transpose ji. That is the very definition of transpose for any arbitrary matrix.
ও হ্যাঁ, ইয়েস ঠিক, বুঝতে পেরেছি।
ওকে, এই ডেরিভেশনে কোনো গোলমাল লাগছে, কোনো অসুবিধা হচ্ছে? আচ্ছা, আরেকটা জিনিস বলে দিই, ট্রেস অফ এ বি হ্যাজ টু বি ট্রেস অফ বি এ। Okay, because trace of AB is summation over I, AB, I, which is summation over I, summation over J, Aij, Bij. Then I can do this. I can change the order of summation. Okay, so if I do change the order of summation, what will happen? Sorry, sorry. It's not Bij, it is Bji. Okay, so Bjiaij. This is basically summation over I. This is basically summation over j. Ba jj, which is basically trace of Ba. A duto result that A inner product B is basically trace of A transpose B, and trace of AB is basically trace of BA. That means this is also trace of BA transpose, and this is trace of AB transpose. Acha. One more thing, if I multiply a matrix with an orthogonal tensor QA Q transpose, okay, and then if I try to calculate the trace of it, because this thing holds that trace of AB is trace of BA, I can segregate that into Q times AQ transpose. So this is trace of AQ transpose times Q, which is trace of A. তার মানে কি দাঁড়ালো যে if I rotate a matrix, trace doesn't change. Okay, so to rotate a vector, I need to multiply with just Q. To rotate a matrix, I need to multiply with Q and Q transpose. And once I rotate, certain quantities do not change. Just like for a vector, the length doesn't change. For a matrix, the trace doesn't change. So trace is an invariant called the I1, the first invariant of a matrix that is not affected by rotation. Okay, and it can be shown that det QAQ transpose is also det A, because you see we have already proved that det AB is det A det B, which basically means det BA. Okay, so we can again do that operation where this is det A Q transpose Q, and this thing boiling down to identity matrix. Okay, so determinant is the third identity, not identity tensor. Third determinant is the third invariant, and that is also called the second invariant. Okay, and you can learn about that, but these are some important results in relation to linear algebra. Might be useful to you someday. Okay, so we'll meet on next Wednesday, and when we do.
স্যার বলছি ভয়েড নোটেশনটা একটু বলবেন?
Void notation is the so-called engineering notation যেখানে stress আর strain কে using the help of the idea that both are symmetric tensors. Okay, of course there is some condition to it, but mostly they are symmetric. What we do is instead of taking 9 components and representing that in a matrix, we say that there are only 6 independent components, so might as well represent them as a 6x1 vector, and that's what is void notation. And when what we do is stress, so sigma xx, sigma yy, sigma zz, then sigma xy, sigma yz, sigma zx. Okay, but when it comes to strain, the shear components are multiplied with 2 and represented with gamma. So gamma xy is twice epsilon xy. And why is it done so? Because many a times in our expression, a strain energy like form pops up. Okay, whether we do variational formulation, whether we do your what is that thing, potential energy, whether we do that thing, what is it called, whatever. In mechanics, a lot of times the strain energy like formulation pops up where you take inner product of stress with inner product of strain. And just the way we discussed, the inner product of two matrices is essentially multiplication of each term in the stress tensor, okay, with the corresponding term in the strain tensor, and then adding them up. So there is 9 terms that has to be added. Okay, but then when I take the in the void notation form, or the the vector representation of the stress and strain, okay, 6x1 vector, 6x1 vector. So there, if I take a dot product, I'm only adding 6 terms. Okay, so I'm multiplying the identically positioned terms and adding them up. So I'm only adding 6 terms, just to take care of the fact that the shear terms appear twice in the stress and the strain tensor, and for that matter in the inner product, okay, because individual terms have to be multiplied and added. So just to take care of that, the shear strains are multiplied with 2. Okay, বোঝা গেল এই অবধি?
হ্যাঁ স্যার, হ্যাঁ।
ঠিক আছে? Okay, so we'll meet on Wednesday, and when we do, we'll be discussing about higher order elements. Okay, we just hinted about 6-noded triangle today. We'll work our way with Pascal's triangles even more, and then we will discuss about higher element, and then we need one class for numerical integration, then another class for hourglass mode, and any advanced topic we may cover. Okay, and I'm not sure if we would be getting any other class. Okay, if we do, probably we would be discussing about thermal conduction at best. Okay, so that's the target. Okay, so let's meet on Wednesday.